Hello and welcome to this tutorial on deep learning. My name is Mohan, and in the next about 1.5 hours I will take you through what is deep learning and into Tensorflow environment to show you an example of deep learning. Now, there are several applications of deep learning, really very interesting and innovative applications, and one of them is identifying the geographic location based on a picture. And how does this work? The way it works is pretty much we train an artificial neural network with millions of images which are tagged, their geolocation is tagged, and then when we feed a new picture, it will be able to identify the geolocation of this new image. For example, you have all these images, especially with maybe some significant monuments or significant locations, and you train with millions of such images, and then when you feed another image, it need not be exactly one of those that you have trained. It can be completely different. That is the whole idea of training. It will be able to recognize, for example, that this is a picture from Paris because it is able to recognize the Eiffel Tower. So the way it works internally, if we have to look a little bit under the hood, is these images are nothing but this is digital information in the form of pixels. So each image could be a certain size. It can be 256 by 256 pixel kind of a resolution, and then each pixel is either having a certain grade of color, and all that is fed into the neural network, and it then gets trained in, and it's able to, based on these pixel information, it is able to get trained and able to recognize the features and extract the features, and thereby it is able to identify these images and the location of these images. And then when you feed a new image, it kind of, based on the training, it will be able to figure out where this image is from. So that's the way, a little bit under the hood, how it works. So what are we going to do in this tutorial? We will see what is deep learning and what do we need for deep learning. And one of the main components of deep learning is neural networks. So we will see what is neural network, what is a perceptron, and how to implement logic gates like AND, OR, NOR, and so on using perceptrons, the different types of neural networks, and then applications of deep learning. And we will also see how neural networks works. So how do we do the training of neural networks? And at the end, we will end up with a small demo code which will take you through in TensorFlow. Now, in order to implement deep learning code, there are multiple libraries or development environments that are available, and TensorFlow is one of them. So the focus at the end of this would be on how to use TensorFlow to write a piece of code using Python as a programming language. And we will take up an example which is a very common one, which is like the hello world of deep learning, the handwriting number recognition, which is a MNIST, commonly known as MNIST database. So we will take a look at MNIST database and how we can train a neural network to recognize handwritten numbers. So that's what you will see in this particular video. So let's get started. What is deep learning? Deep learning is like a subset of what is known as a high-level concept called artificial intelligence. You must be already familiar, must have heard about this term, artificial intelligence. So artificial intelligence is like the high-level concept, if you will. And in order to implement artificial intelligence applications, we use what is known as machine learning. And within machine learning, a subset of machine learning is deep learning. Machine learning is a little bit more generic concept, and deep learning is one type of machine learning, if you will. And we will see a little later in maybe the following slides a little bit more in detail how deep learning is different from traditional machine learning. But to start with, we can mention here that deep learning uses one of the differentiators between deep learning and traditional machine learning is that deep learning uses neural networks. And we will talk about what are neural networks and how we can implement neural networks and so on and so forth as a part of this tutorial. So a little deeper into deep learning. Deep learning primarily involves working with complicated unstructured data compared to traditional machine learning, where we normally use structured data. In deep learning, the data would be primarily images or voice or maybe text file. And it is a large amount of data as well. And deep learning can handle complex operations. It involves complex operations. And the other difference between traditional machine learning and deep learning is that the feature extraction happens pretty much automatically. In traditional machine learning, feature engineering is done manually. The data scientists, we data scientists have to do feature engineering, feature extraction. But in deep learning, that happens automatically. And of course, deep learning, for large amounts of data, complicated unstructured data, deep learning gives very good performance. Now, as I mentioned, one of the secret sources of deep learning is neural networks. Let's see what neural networks is. Neural networks is based on our biological neurons. The whole concept of deep learning and artificial intelligence is based on human brain, and human brain consists of billions of tiny stuff called neurons, and this is how a biological neuron looks, and this is how an artificial neuron looks. So neural networks is like a simulation of our human brain. Human brain has billions of biological neurons, and we are trying to simulate the human brain using artificial neurons. This is how a biological neuron looks. It has dendrites, and the corresponding component with an artificial neural network is, or an artificial neuron, are the inputs. They receive the inputs through dendrites. And then there is the cell nucleus, which is basically the processing unit in a way. So in artificial neuron also there is a piece which is an equivalent of this cell nucleus, and based on the weights and biases, we will see what exactly weights and biases are as we move. The input gets processed, and that results in an output. In a biological neuron, the output is sent through a synapse, and in an artificial neuron there is an equivalent of that in the form of an output. And biological neurons are also interconnected. So there are billions of neurons which are interconnected. In the same way, artificial neurons are also interconnected. So this output of this neuron will be fed as an input to another neuron, and so on. Now, in neural network, one of the very basic units is a perceptron. So what is a perceptron? A perceptron can be considered as one of the fundamental units of neural networks. It can consist at least of one neuron, but sometimes it can be more than one neuron. But you can create a perceptron with a single neuron, and it can be used to perform certain functions. It can be used as a basic binary classifier. It can be trained to do some basic binary classification, and this is how a basic perceptron looks like. And this is nothing but a neuron. You have inputs x1, x2, to xn, and there is a summation function, and then there is what is known as an activation function. And based on this input, what is known as the weighted sum, the activation function either gives an output like a 0 or a 1. So we say the neuron is either activated or not. So that's the way it works. So you get the inputs. These inputs are, each of the inputs are multiplied by a weight, and there is a bias that gets added, and that whole thing is fed to an activation function, and then that results in an output. And if the output is correct, it is accepted. If it is wrong, if there is an error, then that error is fed back, and the neuron then adjusts the weights and biases to give a new output, and so on and so forth. So that's what is known as the training process of a neuron or a neural network. There's a concept called perceptron learning. So perceptron learning is again one of the very basic learning processes. The way it works is somewhat like this. So you have all these inputs like x1 to xn, and each of these inputs is multiplied by a weight, and then that sum, this is the formula, the equation. So that sum, wi xi sigma of that, which is the sum of all these product of x and w, is added up, and then a bias is added to that. The bias is not dependent on the input or the input values, but the bias is common for one neuron. However, the bias value keeps changing during the training process. Once the training is completed, the values of these weights, W1, W2, and so on, and the value of the bias gets fixed. So that is basically the whole training process, and that is what is known as the perceptron training. So the weights and biases keep changing till you get the accurate output, and the summation is of course passed through the activation function. As you see here, this WIXI summation plus B is passed through activation function, and then the neuron gets either fired or not, and based on that there will be an output. That output is compared with the actual or expected value, which is also known as labeled information. So this is the process of supervised learning. So the output is already known, and that is compared, and thereby we know if there is an error or not. And if there is an error, the error is fed back and the weights and biases are updated accordingly till the error is reduced to the minimum. So this iterative process is known as perceptron learning or perceptron learning rule, and this error needs to be minimized. So till the error is minimized, this iteratively the weights and biases keep changing, and that is what is the training process. So the whole idea is to update the weights and the bias of the perceptron till the error is minimized. The error need not be zero. The error may not ever reach zero, but the idea is to keep changing these weights and bias so that the error is minimum, the minimum possible that it can have. So this whole process is an iterative process, and this is the iteration continues till either the error is zero, which is unlikely situation, or it is the minimum possible within these given conditions. Now in 1943, two scientists, Warren McCulloch and Walter Pitts, came up with an experiment where they were able to implement the logical functions like AND, OR, and NOR using neurons, and that was a significant breakthrough in a sense. So they were able to come up with the most common logical gates. They were able to implement some of the most common logical gates, which could take two inputs like A and B and then give a corresponding result. So for example, in case of an AND gate, A and B, and then the output is AB. In case of an OR gate, it is A plus B, and so on and so forth. And they were able to do this using a single layer perceptron. Now, most of these gates, it was possible to use single layer perceptron except for XOR, and we will see why that is in a little bit. So this is how an AND gate works. The inputs A and B, the output should be fired, or the neuron should be fired only when both the inputs are 1. So if you have 0, 0, the output should be 0. For 0, 1, it is again 0, 1, 0 again 0, and 1, 1, the output should be 1. So how do we implement this with a neuron? So it was found that by changing the values of weights, it is possible to achieve this logic. So for example, if we have equal weights like 0.7, 0.7, and then if we take the sum of the weighted product, so for example 0.7 into 0, and then 0.7 into 0 will give you 0, and so on and so forth. And in the last case, when both the inputs are 1, you get a value which is greater than 1, which is the threshold. So only in this case the neuron gets activated and the output is, there is an output. In all the other cases, there is no output because the threshold value is 1. So this is implementation of an AND gate using a single perceptron or a single neuron. Similarly, an OR gate. In order to implement an OR gate, in case of an OR gate, the output will be 1 if either of these inputs is 1. So for example, 0, 1 will result in 1, or rather, in all the cases it is 1 except for 0, 0. So how do we implement this using a perceptron? Once again, if you have a perceptron with weights, for example 1.2, now if you see here, if in the first case when both are 0, the output is 0. In the second case, when it is 0 and 1, 1.2 into 0 is 0, and then 1.2 into 1 is 1. And in the second case, similarly, the output is 1.2. In the last case, when both the inputs are 1, the output is 2.4. So during the training process, these weights will keep changing, and then at one point where the weights are equal to W1 is equal to 1.2 and W2 is equal to 1.2, the system learns that it gives the correct output. So that is implementation of OR gate using a single neuron or a single layer perceptron. Now, XOR gate. This was one of the challenging ones. They tried to implement an XOR gate with a single level perceptron, but it was not possible. And therefore, in order to implement an XOR, so this was like a roadblock in the progress of neural network. However, subsequently they realized that this can be implemented, an XOR gate can be implemented using a multi-level perceptron or MLP. So in this case, there are two layers instead of a single layer, and this is how you can implement an XOR gate. So you will see that X1 and X2 are the inputs, and there is a hidden layer, and that's why it is denoted as H3 and H4, and then you take the output of that and feed it to the output at O5 and provide a threshold here. So we will see here that this is the numerical calculation. So the weights are, in this case for X1 it is 20 and minus 20, and once again 20 and minus 20. So these inputs are fed into H3 and H4. So you will see here for H3 the input is 0, 1, 1, 1, and for H4 it is 1, 0, 1, 1. And if you now look at the output, final output, where the threshold is taken as 1, if we use a sigmoid with the threshold 1, you will see that in these two cases it is 0, and in the last two cases it is 1. So this is the implementation of XOR. In case of XOR, only when one of the inputs is 1, you will get an output. So that is what we are seeing here. If we have either both the inputs are 1 or both the inputs are 0, then the output should be 0. So that is what is an exclusive OR gate. So it is exclusive because only one of the inputs should be 1, and then only you will get an output of 1, which is satisfied by this condition. So this is a special implementation. XOR gate is a special implementation of Perceptron. Now that we got a good idea about Perceptron, let's take a look at what is a neural network. So we have seen what is a perceptron, we have seen what is a neuron, so we will see what exactly is a neural network. So neural network is nothing but a network of these neurons, and they are different types of neural networks. There are about 5 of them. These are artificial neural network, convolutional neural network, then recursive neural network or recurrent neural network, deep neural network, and deep belief network. So, and each of these types of neural networks have a special, they can solve a special kind of problems. For example, convolutional neural networks are very good at performing image processing and image recognition and so on, whereas RNN are very good for speech recognition and also text analysis and so on. So each type has some special characteristics, and they are good at performing certain special kind of tasks. What are some of the applications of deep learning? Deep learning is today used extensively in gaming. You must have heard about AlphaGo, which is a game created by a startup called DeepMind, which got acquired by Google. And AlphaGo is an AI which defeated the human world champion Lee Sedol in this game of Go. So gaming is an area where deep learning is being extensively used, and a lot of research happens in the area of gaming as well. In addition to that, nowadays there are neural networks or special type called generative adversarial networks, which can be used for synthesizing either images or music or text and so on, and they can be used to compose music. So the neural network can be trained to compose a certain kind of music. And autonomous cars, you must be familiar with Google's self-driving car, and today a lot of automotive companies are investing in this space, and deep learning is a core component of this autonomous cars. The cars are trained to recognize, for example, the road, the lane markings on the road, signals, any objects that are in front, any obstruction, and so on and so forth. So all this involves deep learning. So that's another major application. And robots, we have seen several robots, including Sophia. You may be familiar with Sophia, who was given a citizenship by Saudi Arabia. And there are several such robots which are very human-like, and the underlying technology in many of these robots is deep learning. Medical diagnostics and healthcare is another major area where deep learning is being used. And within healthcare diagnostics, again, there are multiple areas where deep learning and image recognition, image processing can be used. For example, for cancer detection, as you may be aware, if cancer is detected early on, it can be cured. And one of the challenges is in the availability of specialists who can diagnose cancer using these diagnostic images and various scans and so on and so forth. So the idea is to train neural network to perform some of these activities so that the load on the cancer specialist doctors or oncologists comes down. And there is a lot of research happening here, and there are already quite a few applications that are claimed to be performing better than human beings in this space. It can be lung cancer, it can be breast cancer, and so on and so forth. So healthcare is a major area where deep learning is being applied. Let's take a look at the inner working of a neural network. So how does an artificial neural network, let's say, can we train a neural network to identify the shapes like squares and circles and triangles when these images are fed? So this is how it works. Any image is nothing but it is a digital information of the pixels. So in this particular case, let's say this is an image of 28 by 28 pixel, and this is an image of a square. There is a certain way in which the pixels are lit up, and so these pixels have a certain value, maybe from 0 to 256, and 0 indicates that it is black or it is dark, and 256 indicates it is white or lit up. So that is like an indication or a measure of how the pixels are lit up. And so this is an image is, let's say, consisting of information of 784 pixels. So all the information, what is inside this image, can be kind of compressed into these 784 pixels. The way each of these pixels is lit up provides information about what exactly is the image. So we can train neural networks to use that information and identify the images. So let's take a look how this works. So each neuron, the value, if it is close to 1, that means it is white, whereas if it is close to 0, that means it is black. Now, this is an animation of how this whole thing works. So these pixels, one of the ways of doing it is we can flatten this image and take this complete 784 pixels and feed that as input to our neural network. The neural network can consist of probably several layers. There can be a few hidden layers, and then there is an input layer and an output layer. Now the input layer takes these 784 pixels as input, the values of each of these pixels, and then you get an output which can be of 3 types or 3 classes. One can be a square, a circle, or a triangle. Now during the training process, there will be initially, obviously you feed this image and it will probably say it's a circle or it will say it's a triangle. So as a part of the training process, we then send that error back, and the weights and the biases of these neurons are adjusted till it correctly identifies that this is a square. That is the whole training mechanism that happens out here. Now let's take a look at a circle. Same way. So you feed these 784 pixels. There is a certain pattern in which the pixels are lit up, and the neural network is trained to identify that pattern. And during the training process, once again, it would probably initially identify it incorrectly, saying this is a square or a triangle, and then that error is fed back and the weights and biases are adjusted finally till it finally gets the image correct. So that is the training process. So now we will take a look at same way a triangle. So now if you feed another image which is consisting of triangle. So this is the training process. Now we have trained our neural network to classify these images into a triangle or a circle and a square. So now this neural network can identify these three types of objects. Now if you feed another image, and it will be able to identify whether it's a square or a triangle or a circle. Now what is important to be observed is that when you feed a new image, it is not necessary that the image or the triangle is exactly in this position. Now the neural network actually identifies the patterns. So even if the triangle is, let's say, positioned here, not exactly in the middle, but maybe at the corner or in the side, it would still identify that it is a triangle. And that is the whole idea behind pattern recognition. So how does this training process work? This is a quick view of how the training process works. So we have seen that a neuron consists of inputs. It receives inputs, and then there is a weighted sum, which is nothing but this xi, wi summation of that plus the bias. And this is then fed to the activation function, and that in turn gives us a output. Now during the training process, initially obviously when you feed these images, when you send maybe a square, it will identify it as a triangle, and when you maybe feed a triangle, it will identify as a square, and so on. So that error information is fed back, and initially these weights can be random. Maybe all of them have 0 values, and then it will slowly keep changing. So as a part of the training process, the values of these weights, W1, W2 up to Wn, keep changing in such a way that towards the end of the training process, it should be able to identify these images correctly. So till then, the weights are adjusted, and that is known as the training process. So, and these weights are numeric values. It could be 0.5, 0.25, 0.35, and so on. It could be positive or it could be negative, and the value that is coming here is the pixel value. As we have seen, it can be anything between 0 to 1. You can scale it between 0 to 1 or 0 to 256, whichever way. 0 being black and 256 being white, and then all the other colors in between. So that is the input. So these are numerical values. This multiplication or the product Wixi is a numerical value, and the bias is also a numerical value. We need to keep in mind that the bias is fixed for a neuron. It doesn't change with the inputs, whereas the weights are 1 per input. So that is one important point to be noted. So, but the bias also keeps changing. Initially, it will again have a random value, but as a part of the training process, the weights, the values of the weights W1, W2, Wn, and the value of B will change. And ultimately, once the training process is complete, these values are fixed for this particular neuron. W1, W2 up to Wn, and plus the value of the B is also fixed for this particular neuron. And in this way, there will be multiple neurons, and there may be multiple levels of neurons here, and that's the way the training process works. So this is another example of multi-layer. So there are 2 hidden layers in between, and then you have the input layer, values coming from the input layer, then it goes through multiple layers, hidden layers, and then there is an output layer. And as you can see, there are weights and biases for each of these neurons in each layer, and all of them keeps changing during the training process. And at the end of the training process, all these weights have a certain value, and that is a trained model, and those values will be fixed once the training is completed. Alright, then there is something known as activation function. Neural networks consists of one of the components in neural networks is activation function, and every neuron has an activation function, and there are different types of activation functions that are used. It could be a ReLU, it could be sigmoid, and so on and so forth. And the activation function is what decides whether a neuron should be fired or not. So whether the output should be 0 or 1 is decided by the activation function. And the activation function in turn takes the input, which is the weighted sum. Remember, we talked about Wixi plus B. That weighted sum is fed as an input to the activation function, and then the output can be either a 0 or a 1. And there are different types of activation functions which are covered in an earlier video you might want to watch. Alright, so as a part of the training process, we feed the inputs, the labeled data or the training data, and then it gives an output, which is the predicted output by the network, which we indicate as y hat, and then there is a labeled data, because for supervised learning we already know what should be the output, so that is the actual output. And in the initial process before the training is complete, obviously there will be error, so that is measured by what is known as a cost function. So the difference between the predicted output and the actual output is the error, and the cost function can be defined in different ways. There are different types of cost functions. So in this case, it is like the average of the squares of the error. So, and then all the errors are added, which can sometimes be called as sum of squares, sum of square errors, or SSE, and that is then fed as a feedback in what is known as backward propagation or back propagation. And that helps in the network adjusting the weights and biases. And so the weights and biases get updated till this value, the error value or the cost function, is minimum. Now there is a optimization technique which is used here called gradient descent optimization. And this algorithm works in a way that the error, which is the cost function, needs to be minimized. So there's a lot of mathematics that goes behind this. For example, they find the local minima and the global minima using the differentiation and so on and so forth. But the idea is this. So as a training process, as the part of training, the whole idea is to bring down the error, which is like, let's say this is the function, the cost function. At certain levels it is very high, the cost value of the cost function, the output of the cost function is very high. So the weights have to be adjusted in such a way, and also the bias of course, that the cost function is minimized. So there is this optimization technique called gradient descent that is used, and this is known as the learning rate. Now gradient descent, you need to specify what should be the learning rate, and the learning rate should be optimal, because if you have a very high learning rate, then the optimization will not converge, because at some point it will cross over to the side. On the other hand, if you have very low learning rate, then it might take forever to converge. So you need to come up with the optimum value of the learning rate, and once that is done using the gradient descent optimization, the error function is reduced, and that's like the end of the training process. Alright, so this is another view of gradient descent. So this is how it looks. This is your cost function, the output of the cost function, and that has to be minimized using gradient descent algorithm. And these are like the parameters, and weight could be one of them. So initially we start with certain random values, so cost will be high, and then the weights keep changing, and in such a way that the cost function needs to come down, and at some point it may reach the minimum value, and then it may increase. So that is where the gradient descent algorithm decides that, okay, it has reached a minimum value and it will kind of try to stay here. This is known as the global minima. Now sometimes these curves may not be, just for explanation purpose, this has been drawn in a nice way, but sometimes these curves can be pretty erratic. There can be some local minima here, and then there is a peak, and so on. So the whole idea of gradient descent optimization is to identify the global minima and to find the weights and the bias at that particular point. So that's what is gradient descent. And then this is another example. So you can have these multiple local minima. So as you can see, at this point when it is coming down, it may appear like this is a minimum value, but then it is not. This is actually the global minimum value, and the gradient descent algorithm will make an effort to reach this level and not get stuck at this point. So the algorithm is already there, and it knows how to identify this global minimum, and that's what it does during the training process. Now, in order to implement deep learning, there are multiple platforms and languages that are available, but the most common platform nowadays is Tensorflow, and so that's the reason we have this tutorial. We have created this tutorial for Tensorflow. So we will take you through a quick demo of how to write a TensorFlow code using Python. And TensorFlow is an open source platform created by Google. So let's just take a look at the details of TensorFlow. And so this is a a library, a Python library, so you can use Python or any other languages. It's also supported in other languages like Java and R and so on. But Python is the most common language that is used. So it is a library for developing deep learning applications, especially using neural networks. And it consists of primarily two parts, if you will. So one is the tensors, and then the other is the graphs or the flow. That's the way the name, that's the reason for this kind of a name called TensorFlow. So what are tensors? Tensors are like multi-dimensional arrays, if you will. That's one way of looking at it. So usually you have a one-dimensional array. So first of all, you can have what is known as a scalar, which means a number. And then you have a one-dimensional array, something like this, which means this is like a set of numbers. So that is a one-dimensional array. Then you can have a two-dimensional array, which is like a matrix. And beyond that, sometimes it gets difficult. So this is a three-dimensional array, but TensorFlow can handle many more dimensions. So it can have multi-dimensional arrays. That is the strength of TensorFlow, and which makes computation, deep learning computation, much faster. And that's the reason why TensorFlow is used for developing deep learning applications. So TensorFlow is a deep learning tool, and this is the way it works. So the data basically flows in the form of tensors, and the way the programming works as well is that you first create a graph of how to execute it, and then you actually execute that particular graph in the form of what is known as a session. We will see this in the TensorFlow code as we move forward. So all the data is managed or manipulated in tensors, and then the processing happens using these graphs. There are certain terms called, like for example, ranks of a tensor. The rank of a tensor is like a dimensionality in a way. So for example, if it is scalar, so there is just a number, just one number, the rank is supposed to be 0, and then it can be a one-dimensional vector, in which case the rank is supposed to be 1, and then you can have a two-dimensional vector, typically like a matrix. Then in that case we say the rank is 2, and then if it is a three-dimensional array, then rank is 3, and so on. So it can have more than 3 as well. So it is possible that you can store multi-dimensional arrays in the form of tensors. So what are some of the properties of TensorFlow? I think today it is one of the most popular platform. TensorFlow is the most popular deep learning platform or library. It is open source. It's developed by Google, developed and maintained by Google, but it is open source. One of the most important things about TensorFlow is that it can run on CPUs as well as GPUs. GPU is a graphical processing unit, just like CPU is central processing unit. Now, in earlier days, GPU was used primarily for graphics, and that's how the name has come. And one of the reasons is that it cannot perform generic activities very efficiently like CPU, but it can perform iterative actions or computations extremely fast and much faster than a CPU. So they are really good for computational activities, and in deep learning there is a lot of iterative computation that happens, so in the form of matrix multiplication and so on. So GPUs are very well suited for this kind of computation, and TensorFlow supports both GPU as well as CPU. And there's a certain way of writing code in TensorFlow. We will see as we go into the code. And of course, TensorFlow can be used for traditional machine learning as well, but then that would be an overkill. But just for understanding, it may be a good idea to start writing code for a normal machine learning use case, so that you get a hang of how TensorFlow code works, and then you can move into neural networks. So that is just a suggestion, but if you're already familiar with how TensorFlow works, then probably you can go straight into the neural networks part. So in this tutorial, we will take the use case of recognizing handwritten digits. This is like a hello world of deep learning, and this is a nice little MNIST database is a nice little database that has images of handwritten digits nicely formatted, because very often in deep learning and neural networks, we end up spending a lot of time in preparing the data for training. And with MNIST database, we can avoid that. you already have the data in the right format which can be directly used for training. And MNIST also offers a bunch of built-in utility functions that we can straight away use and call those functions without worrying about writing our own functions. And that's one of the reasons why MNIST database is very popular for training purposes. Initially, when people want to learn about deep learning and TensorFlow, this is the database that is used. And it has a collection of 70,000 handwritten digits, and a large part of them are for training. Then you have test, just like in any machine learning process, and then you have validation. And all of them are labeled. So you have the images and their label. And these images, they look somewhat like this. So they are handwritten images collected from a lot of individuals. People have, these are samples written by human beings. They have handwritten these numbers going from 0 to 9. So people have written these numbers, and then the images of those have been taken and formatted in such a way that it is very easy to handle. So that is MNIST database. And the way we are going to implement this in our TensorFlow is we will feed this data, especially the training data, along with the label information. And the data is basically, these images are stored in the form of the pixel information, as we have seen in one of the previous slides. All the images are nothing but, these are pixels. So an image is nothing but an arrangement of pixels, and the value of the pixel, either it is lit up or it is not, or in somewhere in between. That's how the images are stored, and that is how they are fed into the neural network and for training. Once the network is trained, when you provide a new image, it will be able to identify within a certain error, of course. And for this, we will use one of the simpler neural network configurations called Softmax. And for simplicity, what we will do is we will flatten these pixels. So instead of taking them in a two-dimensional arrangement, we just flatten them out. So for example, it starts from here. It is a 28 by 28. So there are 784 pixels. So pixel number 1 starts here. It goes all the way up to 28. Then 29 starts here and goes up to 56 and so on. And the pixel number 784 is here. So we take all these pixels, flatten them out, and feed them like one single line into our neural network. And this is what is known as a softmax layer. What it does is, once it is trained, it will be able to identify what digit this is. So there are, in this output layer, there are 10 neurons, each signifying a digit. And at any given point of time, when you feed an image, only one of these 10 neurons gets activated. So for example, if this is trained properly, and if you feed a number 9 like this, then this particular neuron gets activated. So you get an output from this neuron. Let me just use a pen or a laser to show you here. Okay, so you're feeding a number 9. Let's say this has been trained, and now if you're feeding a number 9, this will get activated. Now let's say you feed 1 to the trained network, then this neuron will get activated. If you feed 2, this neuron will get activated, and so on. I hope you get the idea. So this is one type of a neural network or an activation function known as softmax layer. So that's what we will be using here. This is one of the simpler ones for quick and easy understanding. So this is how the code would look. We will go into our lab environment in the cloud, and we will show you there directly. But very quickly, this is how the code looks. And let me run you through briefly here, and then we will go into the Jupyter notebook where the actual code is, and we will run that as well. So as a first step, first of all, we are using Python here, and that's why the syntax of the language is Python. And the first step is to import the TensorFlow library. So, and we do this by using this line of code saying import TensorFlow as TF. TF is just for convenience, so you can give any name. And once you do this, TF TensorFlow is available as an object in the name of TF, and then you can run its methods and access its attributes and so on and so forth. And MNIST database is actually an integral part of TensorFlow, and that's again another reason why we, as a first step, we always use this example, MNIST database example. So you just simply import MNIST database as well using this line of code, and you slightly modify this so that the labels are in this format, what is known as one hot true, which means that the label information is stored like an array. And let me just use the pen to show what exactly it is. So when you do this one hot true, what happens is each label is stored in the form of an array of 10 digits, and let's say the number is 8. Okay, so in this case, all the remaining values, there will be a bunch of zeros. So this is like array at position 0, this is at position 1, position 2, and so on and so forth. Let's say this is position 7, then this is position 8. That will be 1 because our input is 8. And again, position 9 will be 0. Okay, so one hot encoding, this one hot encoding true will kind of load the data in such a way that the labels are in such a way that only one of the digits has a value of 1, and that indicates. So based on which digit is 1, we know what is the label. So in this case, the 8th position is 1, therefore we know this sample data, the value is 8. Similarly, if you have a 2 here, let's say, then the labeled information will be somewhat like this. So you have your labels. So you have this as 0, the 0th position. The first position is also 0. The second position is 1 because this indicates number 2. And then you have third as 0 and so on. Okay, so that is the significance of this one hot true. All right, and then we can check how the data is looking by displaying the data. And as I mentioned earlier, this is pretty much in the form of digital form, like numbers. So all these are like pixel values, so you will not really see an image in this format, but there is a way to visualize that image. I will show you in a bit. And this tells you how many images are there in each set. So the training, there are 55,000 images in training, and in the test set there are 10,000, and then validation there are 5,000. So altogether there are 70,000 images. All right, so let's move on, and we can view the actual image by using the matplotlib library. And this is how you can view. This is the code for viewing the images, and you can view them in color or you can view them in grayscale. So the CMap is what tells in what way we want to view it, and what are the maximum values and the minimum values of the pixel values. So these are the max and minimum values of the pixel values. So maximum is 1 because this is a scaled value. So 1 means it is white, and 0 means it is black, and in between is, it can be anywhere in between black and white. And the way to train the model, there is a certain way in which you write your TensorFlow code. And the first step is to create some placeholders, and then you create a model. In this case, we will use the Softmax model, one of the simplest ones. And placeholders are primarily to get the data from outside into the neural network. So this is a very common mechanism that is used. And then, of course, you will have variables, which are remember, these are your weights and biases. So in our case, there are 10 neurons, and each neuron actually has 784 because each neuron takes all the inputs. If we go back to our slide here, actually every neuron takes all the 784 inputs. Right? This is the first neuron. It receives all the 784. This is the second neuron. This also receives all the 780. So each of these inputs needs to be multiplied with a weight, and that's what we are talking about here. So this is a matrix of 784 values for each of the neurons, and so it is like a 10 by 784 matrix because there are 10 neurons. And similarly, there are biases. Now remember, I mentioned bias is only 1 per neuron. So it is not 1 per input, unlike the weights. So therefore there are only 10 biases because there are only 10 neurons in this case. So that is what we are creating a variable for biases. So this is something little new in TensorFlow. You will see, unlike our regular programming languages where everything is a variable, here the variables can be of 3 different types. You have placeholders, which are primarily used for feeding data. You have variables, which can change during the course of computation. And then a third type, which is not shown here, are constants. So these are like fixed numbers. All right. So in a regular programming language, you may have everything as variables or at the most variables and constants. But in TensorFlow, you have 3 different types: placeholders, variables, and constants. And then you create what is known as a graph. So TensorFlow programming consists of graphs and tensors, as I mentioned earlier. So this can be considered ultimately as a tensor. And then the graph tells how to execute the whole implementation, so that the execution is stored in the form of a graph. And in this case, what we are doing is we are doing a multiplication. TF, you remember this TF was created as a TensorFlow object here. One more level, one more. So TF is available here. Now TensorFlow has what is known as a matrix multiplication or matmul function. So that is what is being used here in this case. So we are using the matrix multiplication of TensorFlow so that you multiply your input values x with w, right? This is what we were doing, xw plus b. You're just adding b, and this is in very similar to one of the earlier slides where we saw sigma xi wi. So that's what we are doing here. Matrix multiplication is multiplying all the input values with the corresponding weights and then adding the bias. So that is the graph we created. And then we need to define what is our loss function and what is our optimizer. So in this case, we again use the TensorFlow's APIs. So tf.nn softmax cross entropy with logits is the API that we will use. And reduce mean is what is like the mechanism whereby which says that you reduce the error. And optimizer for doing reduction of the error, what optimizer are we using? So we are using gradient descent optimizer. We discussed about this in a couple of slides earlier. And for that, you need to specify the learning rate. You remember we saw that there was a slide somewhat like this, and then you define what should be the learning rate, how fast you need to come down. That is the learning rate. And this again needs to be tested and tried, and to find out the optimum level of this learning rate. It shouldn't be very high, in which case it will not converge, or shouldn't be very low, because it will, in that case, it will take very long. So you define the optimizer and then you call the method minimize for that optimizer, and that will kickstart the training process. And so far we've been creating the graph, and in order to actually execute that graph, we create what is known as a session, and then we run that session. And once the training is completed, we specify how many times, how many iterations we want it to run. So for example, in this case, we are saying 1000 steps. So that is a exit strategy in a way. So you specify the exit condition. So a training will run for 1000 iterations. And once that is done, we can then evaluate the model using some of the techniques shown here. So let us get into the code quickly and see how it works. So this is our cloud environment. Now you can install TensorFlow on your local machine as well. I'm showing this demo on our existing cloud, but you can also install TensorFlow on your local machine, and there is a separate video on how to set up your TensorFlow environment. You can watch that if you want to install your local environment. Or you can go for any cloud service, like for example Google Cloud, Amazon, or Cloud Labs. Any of these you can use and run and try the code. Okay, so it has got started. We will log in. Alright, so this is our deep learning tutorial code, and this is our TensorFlow environment. And so let's get started. we have seen a little bit of a code walkthrough in the slides as well. Now you will see the actual code in action. So the first thing we need to do is import TensorFlow, and then we will import the data, and we need to adjust the data in such a way that the one hot encoding is set to true, one hot encoding, right? As I explained earlier. So in this case, the label values will be shown appropriately. And if we just check what is the type of the data, so you can see that this is a data sets, Python data sets. And if we check the number of images, the way it looks, so this is how it looks. It is an array of type float 32. Similarly, the number, if you want to see what is the number of training images, there are 55,000, then there are test images 10,000, and then validation images 5,000. Now let's take a quick look at the data itself, visualization. So we will use matplotlib for this. And if we take a look at the shape, now shape gives us like the dimension of the tensors or the arrays, if you will. So in this case, the training data set, if we see the size of the training data set using the method shape, it says there are 55,000 and 55,000 by 784. So remember, the 784 is nothing but the 28 by 28, 28 into 28. So that is equal to 784. So that's what it is showing. Now we can take just one image and just see what is the first image and see what is the shape. So again, size, obviously it is only 784. Similarly, you can look at the image itself, the data of the first image itself. So this is how it shows. So large part of it will probably be zeros, because as you can imagine, in the image only certain areas are written, rest is blank. So that's why you will mostly see zeros, either it is black or white. But then there are these values are, so the values are actually, they are scaled, so their values are between 0 and 1. Okay, so this is what you're seeing. So certain locations there are some values, and then other locations there are zeros. So that is how the data is stored and loaded. If we want to actually see what is the value of the handwritten image, if you want to view it, this is how you view it. So you create, like, do this reshape, and matplotlib has this feature to show you these images. So we will actually use the function called imshow, and then if you pass this parameters appropriately, you will be able to see the different images. Now I can change the values in this position, so which image we are looking at, right? So we can say, if I want to see what is there in maybe 5,000, right? So 5,000 has 3. Similarly, you can just say 5. What is in 5? 5 has 8. What is in 50? Again 8. So basically, by the way, if you're wondering how I'm executing this code, Shift Enter, in case you're not familiar with Jupyter Notebooks, Shift Enter is how you execute each cell, individual cell. And if you want to execute the entire program, you can go here and say run all. So that is how this code gets executed. And here again, we can check what is the maximum value and what is the minimum value of these pixel values. As I mentioned, it is scaled, so therefore it is between, the values lie between 1 and 0. Now this is where we create our model. The first thing is to create the required placeholders and variables, and that's what we are doing here, as we have seen in the slides. So we create one placeholder and we create 2 variables, which is for the weights and biases. These 2 variables are actually matrices. So each variable has 784 by 10 actual values. Okay, so one for this 10 is for each neuron. There are 10 neurons, and 784 is for the pixel values inputs that are given, which is 28 into 28. And the biases, as I mentioned, one for each neuron, so there will be 10 biases. They are stored in a variable by the name B. And this is the graph, which is basically the multiplication of these matrix multiplication of X into W, and then the bias is added for each of the neurons. And the whole idea is to minimize the error. So let me just execute. I think this code is executed. Then we define what is the y value is basically the label value. So this is another placeholder. We had x as one placeholder and y underscore true as a second placeholder, and this will have values in the form of 10 digit arrays. And since we said one hot encoded, the position which has a 1 value indicates what is the label for that particular number. All right. Then we have cross entropy, which is nothing but the loss function. And we have the optimizer. We have chosen gradient descent as our optimizer. Then the training process itself. So the training process is nothing but to minimize the cross entropy, which is again nothing but the loss function. So we define all of this in the form of a graph. So up to here, remember what we have done is we have not exactly executed any TensorFlow code till now. We are just preparing the graph, the execution plan. That's how the TensorFlow code works. So the whole structure and format of this code will be completely different from how we normally do programming. So even with people with programming experience may find this a little difficult to understand it, and it needs quite a bit of practice. So you may want to view this video also maybe a couple of times to understand this flow, because the way TensorFlow programming is done is slightly different from the normal programming. Some of you who, let's say, have done maybe Spark programming to some extent will be able to easily understand this. But even in Spark, the programming, the code itself is pretty straightforward. Behind the scenes, the execution happens slightly differently. But in TensorFlow, even the code has to be written in a completely different way. So the code doesn't get executed in the same way as you have written. So that's something you need to understand, and a little bit of practice is needed for this. So far what we have done up to here is creating the variables and feeding the variables, and or rather not feeding but setting up the variables and the graph. That's all. Defining maybe the what kind of a network you want to use. For example, we want to use Softmax and so on. So you have created the variables, how to load the data, loaded the data, viewed the data, and prepared everything, but you have not yet executed anything in TensorFlow. Now the next step is the execution in TensorFlow. So the first step for doing any execution in TensorFlow is to initialize the variables. So anytime you have any variables defined in your code, you have to run this piece of code always. So you need to basically create what is known as a node for initializing. So this is a node. You still are not yet executing anything here. You just created a node for the initialization. So let us go ahead and create that. And here onwards is where you will actually execute your code in TensorFlow. And in order to execute the code, what you will need is a session, TensorFlow session. So tf.session will give you a session, and there are a couple of different ways in which you can do this, but one of the most common methods of doing this is with what is known as a with loop. So you have a with tf.session as ses and with a colon here, and this is like a block, starting of the block, and these indentations tell how far this block goes, and this session is valid till this block gets executed. So that is the purpose of creating this with block. This is known as a with block. So with tf.session as ses, you say ses.run init. Now ses.run will execute a node that is specified here. So for example, here we are saying ses.run. Ses is basically an instance of the session, right? So here we are saying tf.session. So an instance of the session gets created and we are calling that ses. And then we run a node within that, one of the nodes in the graph. So one of the nodes here is init. So we say run that particular node, and that is when the initialization of the variables happens. Now what this does is, if you have any variables in your code, in our case we have W is a variable and B is a variable. So any variables that we created, you have to run this code, you have to run the initialization of these variables, otherwise you will get an error. Okay, so that's what this is doing. Then we, within this with block, we specify a for loop, and we are saying we want the system to iterate for 1000 steps and perform the training. That's what this for loop does. Run training for 1000 iterations. And what it is doing basically is it is fetching the data or these images. Remember, there are about 50,000 images, but it cannot get all the images in one shot because it will take up a lot of memory and performance issues will be there. So this is a very common way of performing deep learning training. You always do in batches. So we have maybe 50,000 images, but you always do it in batches of 100 or maybe 500, depending on the size of your system and so on and so forth. So in this case, we are saying, okay, get me 100 images at a time and get me only the training images. Remember, we use only the training data for training purpose, and then we use test data for test purpose. You must be familiar with machine learning, so you must be aware of this. But in case you are not, in machine learning also, this is not specific to deep learning, but in machine learning in general, you have what is known as training data set and test data set. Your available data, typically you will be splitting into two parts and using the training data set for training purpose. And then to see how well the model has been trained, you use the test data set to check or test the validity or the accuracy of the model. So that's what we are doing here. And you observe here that we are actually calling an mnist function here. So we are saying mnist train.next batch. Right? So this is the advantage of using mnist database, because they have provided some very nice helper functions which are readily available. Otherwise, this activity itself, we would have had to write a piece of code to fetch this data in batches. That itself is a lengthy exercise. So we can avoid all that if we are using mnist database, and that's why we use this for the initial learning phase. Okay, so when we say fetch, what it will do is it will fetch the images into X and the labels into Y, and then you use this batch of 100 images and you run the training. So ses.run, basically what we are doing here is we are running the training mechanism, which is nothing but it passes this through the neural network, passes the images through the neural network, finds out what is the output, and if the output, obviously initially it will be wrong, so all that feedback is given back to the neural network, and thereby all the W's and B's get updated till it reaches 1000 iterations. In this case, the exit criteria is 1000, but you can also specify probably accuracy rate or something like that for the as an exit criteria. So here it just says that, okay, this particular image was wrongly predicted, so you need to update your weights and biases. That's the feedback given to each neuron, and that is run for 1000 iterations. And typically by the end of this 1000 iterations, the model would have learned to recognize these handwritten images. Obviously, it will not be 100% accurate. Okay, so once that is done, so this happens for 1000 iterations. Once that is done, you then test the accuracy of these models by using the test data set. Right? So this is what we are trying to do here. The code may appear a little complicated because if you're seeing this for the first time, you need to understand the various methods of TensorFlow and so on. But it is basically comparing the output with what is actually there. That's all it is doing. So you have your test data and you're trying to find out what is the actual value and what is the predicted value and seeing whether they are equal or not, tf.equal, right? And how many of them are correct and so on and so forth. And based on that, the accuracy is calculated as well. So this is the accuracy, and that is what we are trying to see, how accurate the model is in predicting these numbers or these digits. Okay, so let us run this. This entire thing is in one cell, so we will have to just run it in one shot. It may take a little while. Let us see. And not bad. So it has finished the 1000 iterations, and what we see here as an output is the accuracy. So we see that the accuracy of this model is around 91%. Okay, now which is pretty good for such a short exercise. Within such a short time we got 90% accuracy. However, in real life this is probably not sufficient, so there are other ways to increase the accuracy. We will see probably in some of the later tutorials how to improve this accuracy, how to change maybe the hyperparameters like number of neurons or number of layers and so on and so forth, and so that this accuracy can be increased beyond 90%. So what is the TensorFlow object detection API? It is an open source framework which is actually provided by the TensorFlow team, and there are trained models available, and a sample code is also available which we can use in order to easily detect objects in images and videos. This is pretty robust and can detect objects fairly quickly, and this is very easy for people to use as well. People with very less or no knowledge of machine learning or deep learning can also, with a little bit of Python programming knowledge, can actually use this API, this library, to build object detection applications. This is a list of libraries that are required, and they have been shown in the code as well. The exact purpose of each of this library, why it is required, is out of the scope of this tutorial, but we will see in the code as we walk through some of these libraries how and why they are used. The COCO data set. COCO stands for Common Objects in Context. So this data set consists of 300,000 images of 90 most commonly found objects like chairs and tables and so on and so forth. So this model has been trained, or in fact a set of models have been trained on this data set, and this is pretty good to detect the most common objects in the images and videos. So with that, let's get into the code. Alright, so the first part is to import all these libraries, and this we have shown you in the slides as well. Again, a large part of this will be for doing some helper functions and maybe for visualizing the images and so on and so forth. So that's the reason they are required. As I said, the exact details of each and every library probably is out of scope, but these are needed. So as a first step, maybe you just go ahead and include these libraries and run the code, and maybe at a later point we can discuss what each of these libraries does. Now this will work with TensorFlow version higher than 1.4. So if you are having TensorFlow version below 1.4, you may have to upgrade to a higher version. So let me go ahead and execute the cell, and we also need this line of code to make sure that once we run this object detection, the labeled images are displayed within this notebook, and many of you by now must be familiar with this. And we will import a few utility libraries, and you will see that we will be using some of these for visualization purpose. So once the objects are detected, we need to display the information, what that object is, and then what percentage of confidence the model has. So all these details, that's the utility functions that are stored here. And then the next part is to prepare the model. As I mentioned, we will be using an existing trained model. The TensorFlow team has actually provided these models. The one that we will be using is SSD with the mobile net, but you can actually use any one of the ones that are listed in this URL. Let me just quickly take you through this URL. These are a bunch of models, trained models that are readily available for anybody to use. It is open source. And let me scroll down. The only thing is that if there are some of them where the accuracy is much higher but they take longer, and there are some where the accuracy is not so high and they are much faster. So they are faster but the accuracy may not be that very high. So you can play around with some of these, and we in this particular exercise or in this particular tutorial we are using this SSD model, which is SSD MobileNet version 1. So that's the model that we'll be using. So in this cell we are primarily creating a bunch of variables with the various, for example, the name of the model, the path, and so on and so forth, so that we will be using these names in the next step, which is to download this model and install it locally. These are also referred to as frozen models. So once they are trained, and then you kind of extract or you freeze the model. So that's the reason they are called frozen models, so that others can just use this without any further training. So this is where we download and extract our model locally. So this will take a little while. Let me see if I can wait or maybe pause the video and come back once it is done. Might take a little while. Let's see if it completes. I have a pretty high speed network, but even then it takes some time, so that's good. But this part is over. Now let us see this part, and yes, both are done. So once that is done, we need to load some label mapping. Basically what this will do is your model, as you may be aware by now, if you do some classification, the model will actually not give any output as a text. It will give some numbers. So if there are 5 classes, it will say, okay, this belongs to model class 1 or 2 or 3 or 5 and so on, the numbers. Now each of these will obviously, the numbers will not make any sense to the outside world, so we need to do some small mapping. So in this case, let's say 1 may be a chair, 2 may be a table, 3 may be a balloon, and so on. So that kind of number to text mapping we need to do, and that is what is being done in this particular cell. And then we have a helper code which will load the image and convert it into a NumPy array, so that the NumPy array is what gets processed and used by the model to do the detection part of it. So that is what this method is all about. So we will be later on we will be calling that function. And next is preparation for detection. So here we are basically telling where the images are stored and how many images, or what is the naming convention or format of the images. Now if you want, you can modify this code. For example, currently I have test_images as my folder. So let me go and show this to you. So this is under my object detection folder. I have another subfolder where I am storing my images, which is text_images. Now you can rename this folder and give some other name, and then in your code you can probably give that particular name for the subfolder. Similarly, the format of these files, what is the name and format of these files? Here it is in a very simple format, which is the names of the files are like beach 1, beach 2, beach 3, and so on. So I have taken beach as the theme. So I have images which are related to beaches. So this is beach 1, beach 2, and then beach 3. I have a few others, but we will use these 3 for our demo. And so that's what I'm saying here. The name of the images will be beach something.jpg, which is JPEG format, and in this curly braces basically will be filled with either 1, 2, or 3 based on in this particular for loop. Okay, so that is what this is doing. Alright, so the next step is to run inference on these images in a loop, and what we are basically doing here is getting these images one by one and then running through the model to find out what are the objects that can be detected, and then against each of the object a box will be drawn and it will be labeled with the name and the percentage of accuracy or confidence that the model detects these objects. Okay, so that is the function here, and so let me just run that piece of code. And here is basically where we are calling this function. So we are loading these images, and then we are calling this function for each image, and then we are displaying this using the matplotlib library. So let's run this. It will take one image at a time and then detect the images. Now the beauty is that the same format of the code can be used for doing object detection in a video. So we have another video for doing object detection in a video. So most of the code out there will be reused from here, and the only thing is that instead of reading the images from the local storage, we read the frames from the video, and there is a neat little video reader that is available, and it will be shown in the other video. And frame by frame we read the video and then pass on to this function, and it will act as if each of these frames is an image, and then it will do the same object detection on the entire video. So that's in a separate video, just look out for that. And actually the information about that is provided in the cards, the eye symbol. So that's the video object detection in video. That's the separate tutorial. Alright, so now that we have all the pieces together, the last cell is where the whole action takes place. So let's run this and see how it looks. So it will take probably a little while, and there are about 3 images. Let's see what it detects. There we go. So good. So the first one, it has detected a person, and that too with 97% accuracy, which is I think pretty good. Okay, and then the next image, it detects umbrella and chair. There are a few other objects, but it's not able to detect. It has detected umbrella with 63% accuracy, or confidence rather, and the chair with 58%. Again, not bad. Then let's see the next image. So here these are actually balloons, hot air balloons, but the model thinks it is a kite, which is probably not that bad. It sees there's something in the sky, and therefore probably it thinks it is a kite, and it detects that with 65% confidence. Okay, so that was pretty much all I wanted to show you in this particular tutorial about object detection in images. And with that, we come to the end of this tutorial. I hope you liked it, and if you have any questions, if you have any comments, please feel free to write it below. And don't forget to watch the other tutorial which does object detection in a video. Alright, thank you very much once again, and have a great day.
Hi there, if you like this video, subscribe to the Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, click here.